Okay, good morning everyone. So today we're going to start with Nikravesh's body coordinate simulation, the application examples. So up to now we've considered fairly simple multi-body mechanisms, specifically the pendulum rod, so only consisting of a single body. And we were able to apply forward and inverse dynamics to that, and then also a combination of that. So before we perhaps jump into the application examples, there's just a few things that I want to go through, which I touched on in the second part of lecture 4's video. So what we did in the previous lecture is we actually compared I think it was the linear accelerations when we had the forward and inverse dynamics acting on the system simultaneously. What would have perhaps been a bit more intuitive is to compare the actual rotational accelerations. So if we consider the graph figure 1 that we have over here, this is now for the case where we have both a driver motor and an applied torque. And what you'll see is for the driver motor that we specified, we know that the acceleration was 2 pi over 60 radians per second squared. And what we actually see over here is that that driver motor then limits the rotational acceleration. So this rotational acceleration is constant at 2 pi over 60 throughout the entire time interval that we ran it. However, if we just run it for the torque case, and this is now figure 2, then you'll see that instead of just getting a constant rotational acceleration, now we have this oscillatory acceleration over here, with the frequency increasing and the period decreasing. And this is now indicative of what the torque actually does. And we know that the effect of gravity is also going to affect this curve that we have over here. Okay, so the other thing that we also just looked at was, I think it was the combined torque graph that we wanted to look at. So perhaps I'm just going to rerun pendulum rod E. So I'm just going to type in DAP PR_E. If we correct the initial conditions, we can see that that is in line with what we specified. We also see that it starts from rest, so that's fine. And then I think the final time over here was, let's maybe do 3 seconds and then 0.01 reporting time steps. We see how this looks. If I run the post processor and then post plot, okay, so perhaps we should just run it for rather 30 seconds. So if I do that, 30 seconds and a 0.1 second time step. If we then run the post processor and we then look at post plot, I just want to make sure that I'm plotting the okay, yeah, so let me just activate figure 6 over here. And now if I run this one, okay, so I see I made a mistake over here somewhere, but I'll just fix that. But what we'll actually see is that the torque that we have over here, the Lagrange multiplier 3 plus 6, should give you the resultant torque. And then Lagrange multiplier 3 is then your IDA torque, so your inverse dynamic analysis torque that you specify. I think what I actually did over here was to make the torque smaller than it should be. So let me just check under in forces. Yeah, so this is now an example of when I specified the torque as 3 Newton meters instead of the 6 Newton meters. So you'll remember from the graph that we have over here, the IDA torque varies between, I believe it was, yeah, it's 6 and minus 6 if you look at the correct torque that we use. So initially, if you just run the IDA or the inverse dynamic analysis, then you're going to get that it oscillates between 6 and minus 6. So what we expect is if we change this then to 6.0, then the torque that I specify should be in line with the resultant torque. So I'm just going to say clear all, close all again. Just close that. I'm going to run DAP and it's PR_E. sorry, I now type J in over there. So it's dap PR_E, correcting the initial conditions for a 30-second final time, reporting time step of 30 seconds. Okay, if we run post and then post plot, then we can see that the IDA torque, which is now here at the bottom, is now between 0 and -12. And then if I add the 6 Newton meter applied torque, then I can see that the resultant torque oscillates between this 6 and this -6 over here. So this is sort of the minimum that I can specify for my torque as input, 6 Newton meters. If I specify anything smaller than that, then it means that I'm going to sit over here and the resultant torque is most likely going to be larger than that. And what that will cause is then that the pendulum is not going to actually rotate all the way counterclockwise. Instead, you're going to have this very localized oscillatory motion where the torque basically picks up the pendulum, but then it's not enough to overcome the effects of gravity, and then it's going to fall back. And it's going to be this picking up and falling back oscillatory motion that you're going to see the entire time. Okay, so I do think I discussed this in the previous lecture video, so if anything is unclear, you can just have a look at that and just post any questions that you have. With regards to, so that's with regards to the pendulum rod that we then handled. Then before we jump into the application examples, I also just want to perhaps go through the assignment that I posted. So if I go to assignments over here, so you'll see I posted both the assignment 1 write-up and then the rubric as well. So for the assignment, it's fairly straightforward. The idea is just that you have to go and construct your own complex multi-body mechanism. And you'll see the files that we also want to have you submit is then all of the input files. And then if you perhaps use this userfunct.m file or the userforce.m file, you can also submit that and any additional MATLAB files. So if you made any changes to the DAP or the anim or the post files, you can also submit that. So, and then of course we want the PDF report as well. So we're going to use the PDF report for the grading of the assessment. So the important thing over here is once you've actually run the multi-body system, that you compare the results or that you analyze the results and give your interpretations over there as well. And that is then where you can use the rubric with regards to how we allocate marks over there. So if we open, I think I opened the same one now, so let me just check. So this one. Right, so we basically break the criteria up into 3. So the first 30 marks considers the actual complexity of the mechanism and the dynamics that you apply. Ideally, we'd like to see a 4-body or more than 4-body mechanism, since we're dealing with complex multi-body systems. So this then excludes ground as well, and then also utilizing different joints. So up to now, we've only looked at the revolute joint. Today, we're going to look at some translation and combined joints as well. We ideally want to see some different joints being utilized for this case as well. And then, of course, the proposed dynamics not being non-trivial. So are you perhaps applying both forward and inverse dynamics? Are there some applied forces that you want to consider as well in your system? Then the evaluation of the performed analysis as well. So this deals more with the actual kinematics and dynamics. We'd like to see that you employ both kinematics, so the actual motion or the coordinate, the velocity and the acceleration state, and then also considering the dynamics, so extending that to the actual forces of the system. And then for the interpretation of the results, this has to do with your graphs, and are you doing some sort of a validation or sanity check as well. So this is not necessarily doing a sanity check on the initial conditions, but at least showing that the outputs that you get are relevant or are correct. So if you have, let's say, a rectangular trajectory that you want to execute, if I go and plot the actual center of mass of the point that's executing that trajectory, that I do indeed get a rectangular envelope. Okay, so that more or less then encompasses everything that we're going to look at for the assignment. Yes.
Interpretation of results
Yes.
like hand calculations.
Yes. So you can do hand calculations. That would probably be for some sort of an initial condition that you want to check to see if everything makes sense from the post processor that you get out. So you can include that, and then any critical discussions, visualizations of your data, those kind of things as well. Yeah. All right. Any questions? Other questions? Okay. All right. So then I'm going to jump into our application examples. So for today, we're going to look at two suspension systems. And these are probably some of the more common suspension systems that are being used in vehicles. For those who had vehicle dynamics as part of their elective modules in the fourth year, or part of your elective modules for the postgraduate studies, you might be more familiar with these suspension systems and how we go about calculating the vibrational effects of the spring damper systems. So in our case, we're going to focus on example, which is shown in figure 8.1a. It's just extended to 15.6a. And that is the planar representation of a double A arm suspension system. So this is the first example that we're going to look at. And its detailed description and the corresponding data can also be found in section 5.6. And this is what we're going to work with. So this is known as a quarter car model. In other words, we only consider a single wheel with its suspension mechanism over here, and this should be enough information to relate to the other wheels and to the overall vehicle suspension system. Okay, so the double A arm suspension system, if I just expand over here, is one of the more commonly used independent front and rear suspension systems. And it is also known as a double wishbone or a short long arm suspension system. And in that case, we basically have a short arm here at the top, OB, and then at the bottom we have QA, which is your longer arm. When this system is viewed from the front or the back, it exhibits planar motion as a 4-bar mechanism, as depicted in figures 15.6a, so this figure over here. The multi-body system shown in figure 8.1a and 15.6a is referred to as a quarter car representation, which could either be the front view or the rear view of the vehicle. So for modeling purposes, the joints and attachment points are labeled in the shown schematic view of figure 8.1 and 15.6a. Right, so just giving more information over here. So the joints that we're also going to look at is some revolute joint at point O. At point Q, we also have a revolute joint, and this is then connected to this wheel assembly that we have over here, also via revolute joints at A and B. And then here in the middle, we have a coil over suspension system, and that is then connected between points F and E. And you'll see that the actual frame of the vehicle is denoted over here as body 0. And then we have body 1, which is your longer arm, body 3, which is the shorter arm, and body 2, which is the actual wheel assembly. Okay, so the individual multi-body components of this system and the corresponding dimensions are then shown in this figure over here. So we just break everything up and we give it with respect to the actual global coordinate system and then the local coordinate systems on each body as well. So the mass centers for the 3 moving bodies are then denoted as G1, G2, and G3. Okay, then we also need some dynamic properties if we want to relate the dynamics to the actual kinematics of the system. So for that, the mass and roll moment of inertias, the characteristics of the spring damper for the suspension, and the tire spring damper data in the radial direction are also listed in table 15.5 here. So body 0, which is then a quarter of the chassis or the frame, then has a 340 kilogram mass and 325 kilogram meter square moment of inertia. And then for bodies 1, 2, and 3, we have their mass and moment of inertia as well. However, for the body coordinate formulation, we're probably not going to use this body 0 information over here. Reason being, we don't actually consider ground when we set up our bodies. We're only going to focus on bodies 1, 2, and 3. And then we also have some spring information over here. So for the suspension system, the free length, the stiffness, and the damping. And the tire itself also has an underformed radius, a deformed radius at rest, a radial stiffness, and then radial damping as well. So the model assumes that the main frame of the car, or body 0, is stationary. So the moving bodies are then indexed as 1, 2, and 3. And we can have a look at how this is defined in bodies. So if I head back to Octave, we have, let's see, double A over here. So this is just the double A arm suspension. And we first want to look at inbodies.m. So if I just open that one, then you'll see we just specify the 3 bodies that are non-stationary or moving. So we have body 1 with its mass, moment of inertia, and then its coordinates and its angle or starting orientation as well. The same is then done for body 2 and then body 3 as well. Okay, so these B3.R and B3.P, or the coordinates and the orientation angles, we're going to look at how we got that in a moment, but it is one of the given components for this problem. Okay, so then a non-moving XY frame is defined on the ground in a convenient location on body 0. So we also already know from this figure over here, the coordinate system sits over here, and we can see that body 0, which is ground, the relevant points are referenced with respect to this global coordinate system. Then 3 body fixed frames are then defined with their origins at the centers of mass, as shown in figures 8.1 and 15.6b. Points 1 through 11 are defined at the attachment points of the revolute joints, spring damper, and a point of interest C on the wheel. So if you look back over here, I think, okay, I see they don't show it over here, but we're basically going to index each point as 1, 2, or 3. I think they perhaps did it under in points. So if we go to the in points file then, okay, so then you'll see that over here we have, I think, a total of 11 points. Let me just check. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points that we actually have. Okay, and how these points are defined is Q1. So this is point Q on body 1. We know that it's a point structure, so since it's on body 1, we just say Q1.B index, so body index, which is 1, and then we give its local coordinates as well with respect to body 1. And we can see that it's minus 0.24 in the xi direction and 0 in the eta direction. So if we perhaps want to check back on that one, we'll see over here we're talking about point Q on body 1. So since the xi eta coordinate system sits like this, we know that it's in the negative xi direction, and then it's in the center of this rod that we have over here. So it's 0 in the eta direction. So it's also common practice to usually align your xi direction so that it's in line with the actual rod, and then eta is just perpendicular to that rod. And this is now for actual rod mechanisms that we're considering. If you're looking at something more complex like this, your choice of xi eta, yeah, you can choose how to set this one up. You can also rotate this one 90 degrees, but it's more common practice to just align xi in the actual parallel direction of the rod. Okay, so this is then done for all of the other points. So the general convention over here is we first specify the actual point and then the body that we're working on. And you can go through this and check for all the points whether it corresponds to what is given on that diagram. And then we simply group all of it together at the end. Okay, so then once that is done, then we can go to the next point, which is the suspension spring damper, which is represented by a point-to-point force element. The model requires a non-standard point-to-point force element representing the radial force of the tire to be active only when the tire is in contact with the ground. So if it's not in contact, we expect that there's no deformation of the actual of the actual tire. So in that case, we're not going to have any spring or damping effects caused by the tire. So to determine whether the tire is in contact with the ground, we can compute a parameter delta, which is then basically the deformation of the tire, which is equal to y2, so the y coordinate of body 2, minus r0. And this r0 is simply 0.35, or the underformed radius of the tire. So if delta is greater than 0, we know that in that case, since it's greater than 0, it means that y2 will be greater than the underformed radius, and the tire does not contact the ground, and therefore no tire force is applied to body 2. If delta is, however, 0 or smaller than 0, the tire force is computed as a point-to-point spring damper vertically attached between point C and the ground, and the force is applied on body 2. And to illustrate this, we can have a look at in-forces and now a new MATLAB file that we haven't considered yet, user force.m. So if we first look at in-forces, you'll see that we have some standard forces over here. So we first have weight, so the actual weight of the bodies. Then we also have this point-to-point force. So this is simply for the suspension system acting between, if we go back, it will be between these 2 points, points F and E. So this is the point-to-point spring damper mechanism that we're modeling over here. So its data is given. So we simply first specify the actual point indices between which it acts. So point index 9 and 10. If I go back to in points, then you'll see that since we have a list length of 10, we're working with E1 and F0. So those are the 2 points that it's acting between. Then F underscore A, I think it's just an external force or an applied force by the spring damper system. So we simply set that to 0. We don't have any information for that one. So we can leave that at 0. But we do have a spring stiffness, an underformed length, and then a damping coefficient as well. So the nice thing about a point-to-point system is that you can specify your spring and damper as a single force structure. And all of this information is then also given in that table that we have over here. So you'll see for the suspension system, the free length, the stiffness, and the damping coefficient are simply translated to over here. Then S2 is also a force structure, but we now specify it as a user type force. And this is now for the actual tire that we're looking at. So first what I'm going to do is specify the spring stiffness of the tire, the underformed radius of the tire as well, and then the damping coefficient. So I also get that from the previous table. However, since we're referencing a user force over here, I then have to set up a new MATLAB file called user_force.m. And this is then where I can specify the force to be some sort of a complex relation if it's not supported by the standard type of forces that I have available. So what I'm going to do over here is I'm first going to calculate this delta value over here, so the deformation of the tire. So this is firstly bodies 2, so I'm looking at body 2 dot R2, so in other words, in the y direction. Then I'm going to minus forces 2, so this then refers back to the forces file that I have over here. Forces 2 is S2. So if I look over here, I specified K, L0, and DC, so now I can just go and pull them in this file over here. So that will be minus forces 2 dot L0. So it's the y coordinate minus the underformed radius. Once I have this, now I just have to go and check that I apply it whenever del is smaller than 0. So in that case, if del is smaller than 0, Fy is then simply equal to forces 2 dot K, so the spring stiffness multiplied by the deformation, which is del, plus forces 2 dot DC, which is the damping coefficient, times bodies 2 dot R underscore D. And this is also in the 2 direction, in the y direction. So what we basically just have over here is the force is equal to Kx plus Cx dot. That's what we write out over here for that spring damper force. Then we just have to go and write this in a form that we can update the forces on body 2 with. So to do that, I just say FSD is equal to 0 because there's no force in the x direction. I only consider it in the y direction. And then minus Fy because it's in the opposite direction to what I calculated over here. And then I just have to go and update the external forces on bodies 2. So I'm just going to say bodies 2 dot F is then equal to whatever the current external forces are, plus this newly calculated external force due to the spring damper system. Okay, any questions so far with regards to the input files? Okay. All right, so then once we have the forces done, then we can just look at this next point that we have over here. So the model assumes that at an initial time, the wheel is not in contact with the ground. So for the moving bodies, we must provide initial conditions on the coordinates and the velocities. The initial conditions must satisfy the constraints at the coordinates and velocities. And this is something that we looked at in previous lectures as well. If we set up those initial conditions, it's usually good practice to also do some sort of an initial condition correction, just to make sure that all of the bodies are connected and there is continuity across your mechanism. If the coordinates are not satisfying the actual constraints, then you're going to end up with some redundancies, and you're most likely going to have that your mechanism is going to break. So certain components are going to move, certain components are going to remain stationary. If we are not certain that the provided initial conditions are correct, we should ask the program to correct them for us. Since in this model it is assumed that at initial time the bodies are at rest, all the velocities are simply set to 0, or we can leave it default. So if we don't specify it, then it is in any case assumed to be 0. So now we can have a look at exercise 8.1. So we use the following set of initial conditions for the coordinates. And this is now the angles that we first get over here. So phi1 is minus 2.1 degrees. We can relate that back to radians. We can do the same for phi2 and phi3. And then they also give us information with regards to R1, R2, and R3. And this is then the information that we simply populated into in bodies. So you can go and check under in bodies, you'll see that these coordinates and these angles match what was given in the file over here. Okay, so then they tasked us with executing that for 1 second and then observing the actual animation of the system. And we can plot the y coordinate of body 2 versus time. And before we look at the solution, let's perhaps just do that. So I'm just going to head back to my command window just to make sure that I'm working with a clear workspace. I'm just going to say clear all, close all CLC. And once I've done that, I can just say, let's run DAP. And I want to run AA, or the double A arm suspension system. Although we know that the coordinates are correct, it's usually good practice to correct them in any case, since we have some truncation errors or round-off errors that are also present in our original calculations or our hand calculations. So I'm just going to say Y over here, and we can now see that the values that I get over here do correspond to what was given in this file over here. And here you can actually see that phi1 was specified as minus 2.1 degrees. But if we look at the corrected coordinates, it's minus 2.103694. So it adds some additional digits over here to ensure continuity. Okay, so then they said we have to execute it for 1 second. And let's perhaps use a reporting time step of 0.001. Okay. I think what I'm maybe going to do is rather just use 0.01, otherwise the animation is going to run quite long. So let me just perhaps rerun it for this one, and then it's still 1 second, but 0.01 second. Okay, so now if we execute annum. Then I can press G over here. I can just open this one. All right, and we can see that there is still some motion over here in the system, but that initial motion that we had where it basically falls to ground is due to the fact that we specified the tire to not be in contact with ground at the start. So the initial coordinates were higher than ground for the actual tire. Okay, and then it's now difficult to see, but I think the system now basically remains at rest. But what happened is we had some sort of an initial downward force, and then once the spring and damping forces started acting on the system, we had smaller oscillations of this time. So we expect to see this when we plot the actual y coordinates of body 2 as well. So if I just, oops, okay, so I see this one just closed now, so let's just rerun it now. It's this one. Okay, so now we can go and have a look at the actual y coordinates. So I'm just going to run post, and once that is done, I can go and actually plot the y coordinates versus time. So I'm just going to say plot t, comma, and then I'm going to look at the y coordinates. So I'm just going to say r for all the time steps. This is on body 2 that they want, and it's in the 2 direction as well, so y coordinates. Okay, and then I can use perhaps a black line to denote that. Right. Okay, so here we can actually see we're starting with a relatively large amplitude. Once the spring damper or the dissipative forces start acting on the system, we still have some oscillation, but after about 0.4 seconds, we can see that it now dies down, and this y coordinate or body 2 actually remains over here at about 0.32 meters. Okay, so if we then go to the solution, we can also just check it over here. So since these coordinates satisfy the position constraints, there is no need to ask the program to correct them, but we still do just for good practice. However, if we ask the program to correct the coordinates, we still get the same results back, perhaps just with a few more digits, so more accuracy in our solution. The animation then also clarifies that there are no constraint violations at the initial time. So we saw that all of the components were connected and they were moving. Then we can also have a look at the plot of the y coordinate of body 2 versus time. So this is just shown in figure 8.2 again. And this once again matches what we got from the DAP-BC system. Yes. 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 So if you consider your suspension system, so that oil over spring damper system, if it was only a spring and you only had spring stiffness for your wheel as well, you would see more oscillations over here. That would, yeah. So you wouldn't have this dissipation after 0.4 seconds. It would be some oscillatory motion that you have.
So that includes the stiffness of the tire and spring.
Yes. So if you didn't remove the damping on the coil over spring, you would still see some sort of a dissipative force over there. Since it is connected to, I think if we go back, I'm not sure if it was over here. So you have these bodies which are basically connected to one another. So the spring which is connected over here to point E, which is on QA, and QA is then once again connected to your tire system over here. So if you only had a spring stiffness, so no damping on your tire, but you still had damping on your coil over spring over here, you would still see some damping effects, but it would probably not be as excessive as with adding damping to the actual tire. Yeah. Okay, so if we then go back to our solution, so what this plot reveals is that the center of the wheel drops from a height of 0.35 meters and then settles at approximately 0.32 meters after about 0.4 seconds. So that is then when damping took over the system and we saw complete dissipation of that oscillatory motion or that bouncing motion of the actual tire. Okay, so then for exercise 8.2, we can use the following set of initial conditions for the coordinates, and we still define the angles in radians as always. In this case, these are considered incorrect initial conditions. And then they tell us to execute DAP without correcting the initial conditions. So let's perhaps do that. So I'm just first going to say over here, clear all, close all CLC. And then if I head back to the AA arm suspension system and I go to in bodies, then you should see there's two additional incorrect coordinates and orientation angles specified over here. So we're just going to first uncomment them. So to do that, you can just highlight the two rows and you can type Control Shift and R. And then we can just indent them correctly. So I'm just going to do that. And then these ones above it, I'm now going to comment out. So that would be Control and R. And then I can do the same with body 2. And it's dot R and P for the correct conditions. I'm just going to comment out again. And then uncomment the incorrect conditions. And comment out the correct conditions. Okay, so now I'm just going to execute it again. So I'm going to say DAP. It's still A that I'm working with. And now I don't want to correct the initial conditions. So I'm just going to type in. And you'll see it now says redundancy in the constraints. So there's probably going to be some constraints that are not going to be met, or they are going to be overridden and you're going to have some stationary elements, or the system is simply going to break. Now, I think the problem also states that we just have to do it for a final time of 0. So this will then evaluate the equations of motion for only t equal to 0. And then we need to also animate the results that contain only one frame. So if we do that, I'm just going to set the final time to 0, and you'll see it doesn't ask for the reporting time step now. So whenever I set the final time equal to the starting time, it sees it as a static analysis that it's doing, or an analysis at that specific point. Okay, so now I'm just going to execute anim again. And now we can see that these constraints have indeed broken. So now we have that this point, these 2 points over here are no longer connected. Perhaps I should just expand it a bit. And then we also have these 2 points which are no longer connected to one another. And we also see some strange behavior over here with the point-to-point force. It's not really the distance that we expect from the center of mass. Okay, so since we have redundancy in the constraints, this is the type of system that we're going to work with. So we need to either make sure that we specify the correct initial conditions, or if we're not too sure about the initial conditions, we need to perform a correction on those initial conditions. Usually it's just good practice to, in any case, do correction on these initial conditions. Okay, so I'm just going to clear solution. So we observe that all of the constraints are violated. The bodies are separated at the pin joints, and we see this also in this figure 8.3 that we have over here. We may simulate the model again, but this time we should ask the program to correct the initial conditions. So if I do that, I'm just going to run DAP AA, and now I'm going to correct the initial conditions. If I still use a final time now of 0, and I go to anim, then you'll see that now I actually have a system that is connected over here. However, the initial condition correction does depend on what you specify as your input conditions, or what you estimate your initial conditions to be. So in this case, you'll see it's actually lower than what we specified for the original case. So if I now go and perhaps create a plot, so I'm now going to plot it over 1 second again. So let's do DAP AA. Yes, I correct them for 1 second with a 0.01 time step. Okay, so now if I run anim, what I'll actually see over here is that the wheel is now moving upwards. So the initial condition that I specified over there actually assumes that the tire is in contact at the start. So what it does is that spring or damper effect then pushes the wheel back up. So what I'm going to see on the y coordinates of body 2 when I plot that as well is that the wheel is in fact going to move up, and then I expect the dissipator forces to once again plateau or constant the y coordinate out. So I think it's just still running in the background. Yeah, so we'll just wait for that to finish and perhaps move this over here. Okay, so I think while this one is executing, there is just something that I also wanted to specify over here. So you'll see on the actual graph that we have over here, and if you go and plot it with a 0.01 time step, you'll see that you also have these, it basically looks like a sharp edge that it creates at these points. So this is simply because of your reporting time step. If you are not happy with this discretization, so if it's not fine enough to actually give you a smooth curve over here, you can always go ahead and just make your reporting time step a bit smaller. So of course there is a fine line between making it too small, so getting a very accurate answer, and then your computational efficiency. If you make it too small, then the system is simply going to run longer, have perhaps more function evaluations as well. But for this type of exercise, we can clearly see the dissipative forces over here, so we don't have to worry about making the reporting time step much smaller than this. Okay, so just going back over here, we can now see that it completed. So I'm just going to close this one then, and then we can type in post. And now I just want to create another plot of the y coordinates for body 2. Okay, so if I start typing in PL and I press the up arrow, then you'll see it changes automatically to this plot, whatever plot I generated previously. So it's just a shorthand method of quickly plotting a previous plot that you created as well. So if I plot this one, then you'll see that indeed the wheel now started at a lower point. So first I have upward motion, and then the dissipative forces causes after 0.4 seconds the wheel to remain at a constant y coordinate, or yeah, a constant position over here. Yeah. Okay, so that is then once again the effect of the initial condition that I specified. The corrective step that I induced is always based on the estimate that I give as input to the initial condition. Okay, so I don't think there is a plot of this one, but we did simulate it now, and we did see that it basically just shifts. First it moves up and then down instead of down and then up. Okay, so that was then exercise 8.2, and I think this then also wraps up what we wanted to look at for the double A arm suspension. Okay, so any questions before we move on to the next suspension system? Yes. Okay. Oh, the user force one. Okay. So if I go back to this one. Okay, so what they basically specify over here is some sort of a deformation or a displacement of the actual spring. So you're seeing the tire as a spring, so you have some sort of an underformed radius or underformed length for this tire. And then you also have the y coordinate of the actual body over here. So if I calculate the deformation, or the delta of the actual spring or tire, then it's going to be the y coordinate minus the underformed length. And I know if this value is smaller than 0, then it means that I'm going to have a deformation of the tire. So there's going to be some spring or damper effect being induced by the actual tire. So since I also know that the motion is vertical, I'm just going to calculate the y component of the spring mass damper system. So I'm going to say Fy is equal to forces 2 dot k, and what I mean by that is if I go back to in forces, so my forces list over here is 1, 2, so I'm working with S2 that I'm calling, and I'm looking specifically at its L naught value. So I'm saying forces 2 dot, or sorry, this is the K value that I'm looking at. So I'm calling forces 2 dot K, and I multiply that with the deformation, plus forces 2 dot DC, so it's damping coefficient, which I also specified over here. Yes, yes, exactly. Yeah, so, and what I'm basically writing over here as well is just Kx plus Cx dot. And then once I have that, I just set it up into a vector form so that I can add it to the existing external forces acting on the body. Yeah.
I see you didn't add any functions.
Yes. So, yes.
In what scenario can we have like a function for this particular?
Yeah, that's a. I don't really know if there's a specific scenario for something like this, because in this case you, unless you actually know what the velocity profile or the position profile, the displacement profile of the wheel looks like. In this case, it makes more sense that you know the spring stiffness and you know the suspension system's dynamic properties, and you want to perform a forward dynamic analysis, and you want to measure what the actual displacement or the coordinate of your wheel is going to be. So this is sort of a pure example of a forward dynamic analysis. An inverse dynamic analysis I don't really think would be appropriate for this type of problem, because we can't really predict the actual motion of the wheel, but we do know the properties of the springs and the tires. Yeah.
You model the tires of both body and then specify displacement at the point that it makes contact with the ground.
Yes, I think you can. Yeah, the displacement curve that you'll get, well, it depends how you want to model it, but you can also specify a user-supplied function. So this is actually one of the changes that was made from DAP BC12 to DAP, or DAP BC11 to DAP BC12. You can now specify a user function in the same way that you specify a user force. So you can do something like that. In this case, it's just easier for us to actually consider the entire wheel assembly as a single body, but you can break up that assembly into different bodies as well. Yes. Right. Okay, so next up we can then look at the McPherson suspension. So this model is the frontal view of a McPherson suspension system as shown in figure 8.4 and then also 15.7a. So in this case we have, just perhaps zoom out a bit. So we can see it looks a bit different to what we had for the double wishbone suspension. In this case, we have a single rod arm over here, which is then connected between the main frame over here and then this, what we once again consider the wheel assembly. However, in the previous case, we actually had that the center of mass is situated at the center of the wheel as well. So when we plotted, or when we considered the actual motion of the wheel, we simply looked at the center of mass. In this case, we now have a situation where the y from the y coordinates for the center of the actual wheel. Okay, and then we also have this coil over spring damper system over here again. And we're actually going to model this as a body on its own. So previously where we had a link, we're now going to consider an actual body for this coil over spring damper mechanism over here. And in that case, this body over here can then translate along this actual system or body one that we have over here. Okay, so if we look at some background with regards to the McPherson suspension, another common type of the front suspension system in automobiles is then this McPherson strut and link. When this system is viewed from the front or the back, it exhibits a planar motion as an inverted slider crank mechanism. For modeling purposes, the bodies and the attachment points are labeled in the schematic presentation, and we see that in figure 8.4 and 15.7a, so this figure over here. So in this presentation, body 0 is the frame, so we're once again going to consider it as ground. The body 1 is then the wheel assembly, and body 2 is the lower arm. The coil-over shock absorber that includes link 3 acts as a sliding joint or a cylindrical joint in 3D. In our case, a sliding joint is going to be modeled as a translational joint. So sliding joint, translational joints can be used interchangeably. I just want to expand over here as well. So another thing with regards to the McPherson suspension is that the fundamental principles of this system are very similar to that of the double wishbone suspension. Variations of this basic strut and link can then also be found in different automobiles. Okay, so the dimensions of the links and the positions of the attachment points are then given in figure 15.7b again. So we once again break up the system into its different bodies, and we just give the local coordinates with respect to the center of mass, psi, eta coordinate systems. And then for body 0, since it's ground, we also give it with respect to the XY coordinates or the global coordinate system. So the mass centers are once again denoted as G1, G2, and G3. So G1 for the wheel assembly, G2 for this lower link that we have over here, and then G3 will be this link for the coil over spring suspension that we have over there. With regards to the dynamic properties, so the mass and moment of inertia properties are once again given in table 15.6. So similar to the double A arm suspension system, we perform a simulation with this model from an initial state where the wheel or tire is not in contact with the ground. And Nikravesh constructs 3 different models for this system, demonstrating how to take advantage of composite joints for reducing the size of the model. The models contain 3, 2, and 1 moving bodies respectively. Although these models are constructed with different number of bodies and joints, they are kinematically identical. We're going to look at that in a moment, but we specify that they are specifically kinematically identical, not dynamically identical. So depending on the number of bodies you have, your mass and moment of inertia properties are going to change, so you're not going to get the same forces out. Okay, so to illustrate this, we can then look at the first example over here, which is McPherson A. So the individual bodies, the defined points, and the unit vectors of this model are shown in figure 8.5. So we once again just have the broken up bodies over here with regards to all of their local coordinates. But the important thing that I just want to show over here is that we now specify 2 unit vectors. So you'll see this is double bracket 1 and double bracket 2. So whenever we specify a translational joint, we're going to need a unit vector which aligns the 2 bodies with each other. In this case, we're going to use unit vector 1 and unit vector 2. Unit vector 2 is relatively easy to find. It's just going to be in the XY direction over here. Unit vector 1, on the other hand, is a bit more difficult. It's at a weird angle with respect to the chosen local coordinate system. And so we're going to look at how to find that in a moment. So this model consists of 3 moving bodies, 3 pin joints. So the 3 pin joints that we have is at point Q, point A, and then point O as well. Then we have 1 translational joint, so that's just this link over here, which needs to move up and down in this wheel assembly unit vector direction over here. So that one connects bodies 1 and 3 with one another. This model results in 9 coordinates and 8 constraints. The spring damper representing the tire is modeled similar to that in the double A arm suspension model. Okay, so we're going to use the same deformation model over there. So we're only going to change basically the joints that we're going to use, and we also have to specify unit vectors now. So exercise 8.3 says we need to review the input M files for this model and then simulate its dynamic response for 0.4 seconds. So to do that, I'm just going to close these and then we can head to mp_a. I'm just going to open all of its files. Okay, so firstly looking at in animate, you'll see that the x min, x max are once again specified, y min and y max are also given. Just something that I quickly want to go back to for the double A arm suspension. The in animate file that we used over here, we actually specified a point C2 as well. So this point is simply for illustrative purposes. Whenever we specify a point under in animate, we just use it to illustrate some motion. We're not actually going to use it in our calculations. And then we can also go and change the colors of the bodies. So body 1 in this case was red, body 3 was blue. Okay, but in our case for the McPherson A suspension system, we can just specify x min, x max, y min, and y max. So these are already given, so we can assume that this is a fair interval to actually animate the system over. Then for in bodies, we once again have the 3 body structures that we specify, and then we have the coordinates and orientations, initial orientations for these bodies, and then their mass and moment of inertia properties as well. And then I just grouped them all together in the bodies list at the bottom. In forces, you'll see looks more or less the same. I once again have a point-to-point force, and this is now between point index 2 and point index 4. So if I go back to in points, point 2 is then point B1, so point B on body 1, and point 4 is then point O on body 0. Okay, and then the second force that I have is then the user supplied tire force that I have. So if I go back to user force, you'll see that this is essentially the same as what I had for the double A arm suspension system. Okay, in funct is still an open list over here, so I don't have anything specified as a driver motor over here. Then in joints, I specify the 3 revolute joints that I have, but now I have this initial or this additional translational joint as well. So this is then J4, and for a translational joint, I need to give it a U or IU index and a JU index, so the 2 unit vector indices. And then together with that, I also need to specify the 2 points along which these translational joints are working. So to illustrate this, we can go to the in U vectors over here. And now you'll see that if I specify a unit vector, I first start off by specifying it as a unit structure. Then I have to specify on which body the unit vector is applicable. So in this case, it's on body 1. And then I also have to give the unit vector on the local coordinate system for this V1. So that would be V1.u local. And this is now 0.47 minus 0.88. So to illustrate how I got that, if we go back to our drawing over here, you'll see that my unit vector that I have over here is in this direction, so between B and A. So what I can do if I want to calculate the unit vector is I calculate the vector BA. Once I have that, I simply divide by the magnitude of the vector. So to do this, I can perhaps go, open up an Excel spreadsheet. So let's do okay, so if I look at in the X direction and in the Y direction, then I can specify BA. So if I look back at my drawing that I have over here, I can see that from B to A, it's 0.17 meters in the X direction, and then in the Y direction from B to A, it would be minus 0.25 meters. So I'm just going to say over here 0.17. and minus 0.2, I think it was 0.25. Let me just double check. Okay, I see it's yes, yeah, so it would be, I think, actually minus 0.25 and then minus 0.07 as well, something like that. Right, and then I can just go and find the magnitude as well. So I'm just going to say mag, and that will then be equal to, I think it's the square root of whatever x is squared plus whatever y is squared as well. All right, and then lastly, I can find the unit vector. So I'm just going to say uvec, and that will then be equal to the x value divided by this value, and then the y value divided by the magnitude as well. Okay, so I get 0.47 and minus 0.88. If I just check back over here, I can see that that is indeed what I got over here. I just rounded it off over here, but I don't expect it to be too much of an issue. I will in any case do initial condition correction and make sure that everything is connected. So the rounding shouldn't be too much of a problem. Okay, and then V2 is then on body 3, and we said if we go back to this one, on body 3, its unit vector is simply aligned with the xi direction. So if I specify its unit vector, it's going to be in the xi direction. So it's just going to be 1 semicolon 0. Once I've specified the two unit vectors, I just group them together once again in the list. And then I can go back to in joints. So now that I have the two unit vectors specified, I now need to specify the 2 points between which the translational joint is going to act. So in this case, I specified it between point index I, point index j, which is 2 and 8. And if I perhaps rather go back to this one, then we can see point 8 is point O on body 1, and point 2 is point B on body, this was point 8 on body 3, and then point 2 is on body 1 at point B. Okay, so I'm creating a translational joint between point O and point B. And then I also just have to make sure that if I specify IU index on body 1, then I point index also needs to be on body 1. So to do that, I just check IP index is 0.2. So if I go to in point, I can see that 0.2 is indeed also on body 1. So that's fine. And then the second point was on body 3. So if I head to the joints, I can see that JU index is on body 3. So JB index should also be on body 3. That's 0.8. So if I go over here, I have 1, 2, 3, 4, 5, 6, 7, 8. So 0.0 on body 3. So that's also fine. So just make sure that your I indices or your I bodies match and that your J bodies match when you specify the translational joints. Okay, so once that is done, then I've set up everything. So then I can actually just go and run this case. So I'm going to say clear all, close all. Then I'm just going to rerun DAP. I'm going to say MP on underscore A. Yes, I want to correct the initial conditions. The final time I believe was 0.4 seconds. So I'm going to use a reporting time step of 0.005 seconds. Okay, so now I can just go and animate the system as well. Right, so now we can once again see that initial downward motion because the tire is not in contact. And once it reaches contact point, then the spring and the damper effects of the tire is going to dissipate that y coordinate motion. And then we expect to see this constant position case over here. Right. So once that is done, I can then go and run post. And I just want to check what they want us to plot as well. So we now view the animation, and then we want to plot the coordinate and the velocity of body 1, or point C, versus time. So let's perhaps first do it for body 1, so in other words, just the center of mass. And to do that, I'm going to head back over here, and I'm going to say plot. Against time, it's going to be R, all of the points for body 1 in the 2 direction, or in the Y direction, and let's perhaps use a black line for that one. Okay, so if I plot this one, okay, I think it just have to close that plot. If I run it again, right, so then we can see once again the initial downward motion of the wheel, and then we have this dissipation over here, meaning that we have a constant Y coordinate for body 1. If I want to perhaps plot the velocity as well, then I can simply change this to RD. I can plot it again, and we can once again see it starts from rest, then the velocity is downwards, and then once it reaches the bottom, the velocity is then going up again, and it's going to be positive until it dissipates, and we once again have a 0 meter per second velocity over here. Okay, so then they also asked us to plot the point C's velocity and coordinates, so I'm just going to do that as well. And to perhaps illustrate that, I'm just going to open the workspace a bit larger, and what we'll see for the RPD, so we're going to use RP and RPD to plot it. So RP is an 81 by 8 by 2 vector that I have over here. So 81 is the number of time steps that I have, 8 is the number of points that I specified, and 2 is simply the X and Y coordinates for each point. So what I'll need to do is go and define or check what point I'm interested in. So they said for point C on body 1. And if I open this one, okay, so I think what they did was to, okay, this was under double A arm, so I should probably look at this one over here. So if I open this one, then I can see it's 0.3 that I'm interested in. Okay, so what I'm going to do is I'm just going to say plot, once again against time, and then I'm interested in the coordinate of the point. It's for all time steps, but it's 0.3 that I'm interested in, so point C, and it's in the 2 direction, in the Y direction. And then I can plot it as a black line again. Right, and now we can see this graph over here. So the overall curvature of the graph looks more or less the same as what we had for the center of mass. But you'll notice if you go and plot the center of mass, its initial coordinates and where it's going to actually plateau is going to differ from point C's coordinates.
And you got yes. The angle of the connection arm to the wheel.
Yes.
How does it interpret that angle? Is it with reference to what?
So it will always be with reference to the positive x-axis. Yeah. So you might
calculate the angle based on. Let's say your body 1 has 3 points on it.
Yes.
Which angle is it?
Oh, okay, yeah. So so what it will then do is it will actually calculate the angle of this psi eta coordinate system. So in this case, since we're only moving up and down, your xi direction is always going to be horizontal. So you do expect to see a 0 angle if we look at that. Yes. Yeah, so if you're interested in the actual angle of this, let's say this unit vector over here, or the direction of the link, then you can go and actually use the orientation angle of this link 3 that you have over here. I think it will probably give it as a negative angle, since you're now going to place point O over here. So yeah, so it should be a negative angle that is going to report back in radians. Right, and then if we also want to plot the velocity of this point, then we're simply going to use RPD, and now we can see this velocity profile over here as well. And once again, the velocity profile will probably differ a bit from what we saw for the mass center. Okay, right, so any questions so far? This first model. Okay. All right, so I think that wraps up MP_A then. So the next one is then McPherson B that we want to consider. So the individual bodies, the defined points, and the unit vectors of this model are then shown in figure 8.7. And we now have this figure over here, and what you'll notice the difference now is we don't have this link over here. Originally we had link OB, which was on its own a body. In this case, we now neglect that body. And what we also had was a revolute joint and then a translation joint over here as well. Now we're going to try and combine those two joints into one. So this model consists of two moving bodies, so the wheel assembly and then this bottom link over here, body 2, two pin joints, so in other words this pin joint over here and this pin joint over here as well, and then one revolute translational joint, where body 3 from the first model has been combined as a massless link with the pin joint O and the translational joint to form a revolute translational joint. So this model then yields 6 coordinates and 5 constraints. It's a bit more computationally efficient than what we had for the previous case. The program constructs a vector between O and B and another vector between B and A, and then it enforces the two vectors to stay parallel. So for exercise 8.4, we're once again going to review the .m files that we have, or the input files. I'm first just going to clear the workspace over here, and then just close the ones that we had for the first model. And then if we go to MP_B, we can open all its files again. Okay, so in animate remains the same. We once again have our minimum and maximum bounds over here, which we can assume is fine. In bodies has now, however, changed. Previously we had 3 bodies, now we only have the 2 bodies, so we have the wheel assembly and then that bottom link as well, which is then body 2. Then for in forces, we still have our point-to-point force, which then acts between points B1 and O0. And then we also have our user force for the tire, which is exactly the same as what we had for the previous 2 models that we looked at. Then under in funct, it's still an open list because we don't have any functions or drivers that we want to specify. Now in joints also changed. So we still have our 2 revolute joints, which are specified. If we go back to this drawing over here, we still have our revolute joint, which is specified at point Q, and another one at point A, but now we have something known as a revolute translational joint that is specified between points O and B. So I simply combine the two independent joints that I had previously. And for this, I then need to specify the 2 points between which the revolute translation joint works. So this is then given as points 2 and 4. If I go back to in points, point 2 will then be point B on body 1. Point 4 will be point 0 or point O on body 0. And then I also just need to give it a IU index. So this should also still be on body 1. So I still match my I body index with that of the I, or the body of IP index with the body of IU index. So if I go to in U vectors, you'll see I'm still specifying it on body 1, and it's still going to be that unit vector that we specified previously. So since I'm now working with one less body, I just have to specify the remaining unit vector on the remaining body. Okay. Right, so once I have that in, then I think that more or less wraps up everything that we wanted to look at for the MATLAB input files. So then it says view the animation and then plot the coordinate and velocity of body 1 or point C versus time, and we're going to plot it for 0.4 seconds, and we can once again use a 5 millisecond step over there. So over here I'm just going to say gap MP underscore B. I'm going to correct the initial conditions, use a final step of 0.4 seconds, and then a reporting time step of 0.005. Okay, so if I run the animation again, then we can see that the previous link has also now been replaced with this dashed line over here. So this just indicates that we're working with the revolute translation joint. And if I run it, we can once again see the initial downward motion, and then once it reaches ground, we see those dissipative and damping forces acting on the system. Okay, so I'm just going to try and close this one. Right, so and then if we plot for body 1 again, so I'm just going to say plot T R for all of the points on body 1 in the Y direction, and we can use a black line for that. I should just close the previous, let's just say close all. Okay, so we see more or less the same kinematic relationship over here. So you can go and compare this with MP underscore A. It should give you exactly the same kinematic or coordinate relation that you have over here. If we then also look at the velocity of that point, or the center of mass, once again we have it starting at 0, and then once the dissipative forces have limited the motion, then we can see we have 0 meters per second velocity at the end. Okay, and then once again we can go and plot the points as well. So to do that, I'm just going back to, I think it's the in points, and they wanted us to plot point C1. So it's still point 3 that I want to plot. So over here I'm just going to say plot T RPD. Let's first do just the coordinates, so RP. If I plot that one, sorry, I now plotted RPD, so let's just redo this one. Okay, so then we see this curvature again. So overall the curvature looks the same, but it starts at a different point over here, depending on the actual point that you selected. And lastly, we can also plot RPD. And we once again have this velocity curve over here. So an initial downward velocity, since the tire is moving down, and then once it reaches ground, then it's going to have some sort of a bouncing effect over here, and that's where we see the upward velocity, a little bit downward, and then once again the velocity is 0, where it then reached equilibrium, or where the tire is then stationary in the Y direction. Okay, so that is then McPherson B. So we now saw that the kinematics look more or less the same, but we are now able to actually be more computationally efficient if we're not interested in the dynamics. So we can reduce the number of bodies that we're interested in. Right, so now we have one last model to look at, McPherson C. And for this case, what we're basically going to do is still use the revolute translation driver that we specified, or the joint that we specified previously. But now we are also going to replace these two revolute joints with a single joint. So where we had one revolute joint over here, one revolute joint over here, we can now combine them to form a revolute-revolute joint. So the model consists of one moving body, which is simply the wheel assembly that we have over here, one revolute-revolute joint, which is between Q and A, and then one revolute translation joint, which is between point O and point B over here. So body 2 from the previous models has been combined with the pin joints Q and A as a massless link to form a revolute-revolute joint. This model results in 3 coordinates and 2 constraints. And the program constructs a vector between points Q and A and enforces the length of the vector to remain a constant 0.45 meters. So where we got this 0.45 meters is actually from the previous link that we had. So this one specifies it as 0.45 meters, so we just have to give that as an input for the revolute joint. So exercise 8.5 then once again tasks us with reviewing the MATLAB input files for this model, and we want to simulate the dynamic response for 0.4 seconds. We're once again going to look at the animation, and then we also want to plot the coordinate and velocity of body 1, and then also for point C on body 1. Right, so to do this, I'm just going to once again close all of these input files for the previous model, and then open MP_C. Right, so in animate once again remains the same, so nothing new over there. In bodies has now been updated, so now we only have a single body, which is our wheel assembly. So we just specify all of its starting coordinate, mass, and moment of inertia properties. Then the forces remain exactly the same. We still have a point-to-point force, a user-defined force for the tire spring stiffness, and then also the weight. In functs is still an open list because we don't have any drivers that we specify. Now in joints changed, so where we previously had 2 revolute joints, we now simply have a revolute joint over here. And in this case, all that we have to specify is the 2 points between which this revolute joint exists. So in our case, we're working with points 1 and 5. So if I go to points, then point 1 is A1, so point A on body 1, and then point 5 is point Q on body 0. And that is indeed the 2 points that it is acting between. And then lastly, I also just have to give the length, so the distance between the 2 points that have a revolute joint. And then lastly, we still have the joint structure J2, which is a revolute translation joint, and this remained exactly the same as what we had for MP_B. Right, so with all of that then done, now we can rerun DAP, and we're going to do it for MP_C. We're going to correct the initial conditions. Final time is still 0.4, and the reporting time step is still 0.005 seconds. Okay, so if I then visualize it with animate again. Right, so before I perhaps do that, just to note over here, so now we have the revolute translation joint, which is denoted by this dash line over here. And then this cyan line that I have over here combines the 2 revolute joints. So I no longer have that link or that black line over here. Now if I run it, and I open it up, we can once again see the initial downward motion. Once it reaches the bottom, it moves up a bit, and then it remains stationary for the remainder of the motion. Okay. Right, so then I'm just going to run post again, and I can once again go and plot the points. So I'm just going to type in plot and navigate to body 1 over here. Once again, just have to close the animation pane. Okay, and we can once again see this relation over here, which looks the same as what we had for the previous 2 cases. If I then go and check the velocity, it should also give me the same profile. And we can see that is indeed the case. So it starts at 0, ends at 0 after about 0.2 seconds, so that's fine. And then I also just have to go and plot point 3, which I still believe is point C. Yeah. Right, so this also looks the same as what we had previously. And then lastly, RPD, which will be the velocity of that point, also looks the same as the previous curvatures that we had for MPA and MPB as well. Right, so if we're not too interested in the dynamics, we can, in other words, combine some of the joints together to make it a bit more computationally efficient. If we are, however, interested in the dynamics, so if I if I'm perhaps interested in what the output force or something would be, then it would most likely change due to the actual masses. I'm currently using massless links, where if I use links that actually have a mass appended to it, then it means I'm going to get different force outputs due to the weights having an effect as well. All right. Okay, so any other questions? Okay. Right, so I think that then wraps up everything for the McPherson strut that we wanted to look at. Yeah, so that is then the two suspension systems. So I think for the next lecture, we're also going to then focus on, I think a few other cards that we want to look at over here. So how we can actually model disc joints as well and have no slip conditions over there. But for the suspension systems, this more or less wraps up everything. So yeah, we'll then continue next week, Thursday, with our application examples. Right, thanks.